All right, so in this example, we're gonna do another 3-bar truss example. I'm gonna go a little faster this go around to kind of accelerate this process just a little bit, but we're gonna jump right into another example. And here I want us to compute the member forces. And so here we're gonna have a roller oriented in a vertical direction. And then here we're gonna have a pin. And draw this a little nicer. There we go. And we're gonna make this top dimension 2 meters. We're gonna make this dimension 1.6 meters. And we're gonna say that we have a point load here of 20 kilonewtons. And then we have another point load here going to the right of 40 kilonewtons. Okay, and let's go ahead and give these some names. We're gonna say that the roller is A, the pin is B, and the free joint is C. So we have 3 members and 3 joints again, and we're gonna use method of joints similar to the last example. So under solution, I'm gonna make a few observations. The first thing is, if you notice the dimensions of this truss, they're not as user-friendly as the previous example was. So if I were you, I would go ahead and maybe calculate this interior angle right here. You don't have to, but I'm gonna go ahead and do it and call it theta. So I'm gonna say theta equals arctangent of opposite over adjacent, so 1.6 meters over 2 meters. And when you crank that through, I get 38.66 degrees. 38.66 degrees, okay? The next question we wanna ask and kind of point out is, again, about external support reactions. We can solve for externals first, but we do not need them since at joint C we have 2 known forces and 2 unknown forces. And what are those 2 unknown forces? Well, that would be the force in AC and the force in BC. Those are the 2 unknown forces referencing joint C. So I'm going to begin at joint C because that's the best place to start, and I can avoid my external support reactions. So I'm going to say, look at a free body diagram of joint C. All right, so what do we have at joint C? Well, at joint C, we have this 40 kilonewtons, right? And then we have 20 kilonewtons going down. And then we have a force in AC going to the left, F sub AC. And then we have a force in BC pointing into quadrant 3. And remember, why am I pointing these forces like this? Well, remember, these are assumed directions. If you refer back to the background video, the best way to go about analyzing a truss is assuming a direction of our forces as pulling away from the joint, pointing away from the joint. That assumes a tensile effect, okay? And just to be proper in our free body diagram, you need to include this angle right here, which we computed as 38.66 degrees just a few minutes ago. So here we go. We're gonna, to get the ball rolling, we're gonna apply our two particle equilibrium equations. I'm gonna say sum of the forces in the x direction equals 0, and I call things pointing to the right as positive, okay? So I'm gonna say negative FAC minus FBC times the cosine of 38.66 degrees, and then plus 40 kilonewtons equals 0. Not a whole lot else we can do here because we have two unknowns. Now I want to take this point right here to explain something that may be a source of confusion. I've seen other people get confused by this in the past. So we've said that if we assume the unknown forces are pointing away from the joint, we're assuming tension, right? And we call tension positive. So what in the world is going on here where we have these negative numbers in front? What's going on? It seems like I'm contradicting myself. Well, no. We actually have two different sign conventions that are working together, and that's important to understand. One sign convention is assuming a tensile effect, which means that the forces are pointing away from the joint. That is tension, and we call tension positive. That is one sign convention. The second sign convention that's in play here is what we call positive in terms of directionality, which is defined by this little guy right here, okay? So that's the second sign convention. What is positive in terms of which way a force is pointing? So in one sense, yes, I'm assuming FAC and FBC are pointing away from this joint, which means tension positive, okay? That's one sign convention. The other sign convention is what do I call positive and negative in terms of directionality? Well, I call things that point to the right positive, which means that if something is pointing to the left in a mathematical equation, I should put a negative sign in front of it, okay? So we need to make sure we understand that, all right? And I'll probably emphasize that in later calculations as well. So let's keep moving. Let's say sum of the forces in the y direction equals 0. And we call, based on our sign convention for directionality, up as positive. So in this case, I'm going to have minus FBC times the sine of 38.66 degrees. And then minus 20 kilonewtons equals 0. FAC and then the 40 kilonewtons don't come into play because neither of them have a vertical component. So I can solve for FBC directly from my vertical equilibrium equation, and that ends up being 20 kilonewtons divided by sine of 38.66. And when I do that, I get a negative 32.02 kilonewtons. And what does that negative indicate for us? Well, that negative indicates compression, 32.02 kilonewtons in compression, which means that FBC is actually going to be pointed at the joint, okay, at joint C. And we're going to redraw that free body diagram right now, actually. So in reality, what we have is a freshly drawn free body diagram with 40 kilonewtons here, 20 kilonewtons here, and then FBC is pointing at the joint, 32.02 kilonewtons, and then FAC is pointing away from the joint right here, FAC, okay? And then here's my angle, 38.66 degrees. All right, so all I did was I redrew my free body diagram with FBC pointing at the joint because we calculated a negative, which indicates it's pointing in the opposite direction, i.e. compression. Okay, now we can substitute this value into our X equation here. All right, now here's where you got to be very, very, very careful. Okay, this is going to be a big source of error. All right, if you substitute 32.02 into FBC here, you have to be extremely careful with how you're accounting for this negative sign. Okay, if you reference the original equation, okay, if you reference the original sum of the forces in the x direction equals 0 equation, then you must incorporate the negative from negative 32.02 kilonewtons, ... Okay, and the reason why is because this equilibrium equation was written in reference to this free body diagram, which shows FBC still pointing down and to the left. Okay, so if you decide to plug in the 32.02 into this equation, you gotta plug it in as negative 32.02 inside of here, and then that'll flip the sign. Okay, so let's do it both ways and show how that works. Okay, so to reference the original free body diagram, the original equation, I'm going to say minus FAC minus a negative 32.02 kilonewtons times cosine 38.66 degrees, and then I believe we had plus 40 kilonewtons equals 0. Okay, so this negative sign, this negative sign that I've circled right now is this negative sign. That is the same negative sign, okay? Now, the negative sign right up next to the 32.02 is this negative sign. So those are two different negative signs. When you plug them in together, it'll become a net positive. So when we rearrange this, we should get FAC equals the following. I'm plugging this into my calculator, so maybe you should plug it in too and make sure you get the same thing I do. Can you hear me punching it in my calculator? So when I punch this in, I get FAC is 65 kilonewtons, and I get a positive, okay? Because I've moved FAC to the other side of the equation, and this negative times this negative gave me a positive, which I combined with the positive 40. So I get a positive 65 kilonewtons in tension, okay? Positive indicates tension. Now, what if we reference the new free body diagram, okay? To reference the new free body diagram, which is this right here, the quote-unquote in reality, notice that this 32.02 is pointing in the opposite direction as it did from the original free body diagram, okay? So to reference the new free body diagram, you need to write an updated sum of the forces in the x direction equals 0 equation. Let's do it. Let's do it for exercise purposes, okay? So we're going to say sum of the forces in the x direction equals 0. And looking at the new free body diagram, we still have negative FAC, and we still have a positive 40, but now we're going to have positive 32.02 kilonewtons, because look at this. Its x component is pointing to the right because the force is pointing into quadrant 1. So here we would say minus FAC plus 32.02 kilonewtons times cosine 38.66 degrees plus 40 kilonewtons equals 0. Ah, look at this. Does this equation come out to be algebraically equivalent to this one? The answer is yes. Look at that. You have positive 32.02. Now, where in the world is this positive coming from? Again, it's referencing the new free body diagram where 32.2 is pointing into quadrant 1. So no matter which free body diagram you look at, if you keep track of your signs properly, you should get the same answer. 65 kilonewtons in tension is FAC. Now, you do not have to do both of these calculations, okay? You don't need to analyze the old free body diagram and then reanalyze the new free body diagram like I did here. I showed both of these calculations just to show you that there are two ways of doing it, okay? But you need to be careful what you're looking at, okay? And you need to substitute in a negative if you're looking in maybe the original free body diagram. So just be very careful there, all right? So at this point, like I said in a previous video, I like to kind of put a check mark by the values, the members that I calculated. So I got AC done and I got BC done. So which joint should I go to next? Should I go to A or should I go to B? Well, again, you got to ask yourself, which joint has at least one known and at most two unknowns, okay? So what's the answer to that? Well, the answer is go to A, okay? B has too many unknowns. You still technically do not know BX and BY, and you don't know FAB. You've got three unknowns at B, but you only have two unknowns at A. You've got AX right here, and then you've got FAB. All right, so we're gonna move to joint A. We're gonna move to joint A since there is two unknowns, okay? So if we look at joint A, here's joint A. What are the two unknowns? Well, one of them is AX, that external support reaction that we said we don't really need to get, but we could if we wanted to. And then we have here FAB. And then what else do we have coming off of A? We have FAC, which we figured out was 65 kilonewtons in tension. So tension means it's pointing away from the joint. So that was 65 kilonewtons. And again, you can look at it as when we were at C, we did the calculations. FAC was positive, so it is pointing to the left. Okay, right? FAC is pointing to the left in this free body diagram. And so that means it must be pointing in the opposite direction when you're looking at the other side of the joint. Okay, so here we can say some of the forces in the X direction, some of the forces in the Y direction equals 0. And when we do that, we should end up getting FAB is 0. Okay, nothing else is in the Y direction, just FAB. And if we wanted AX, we definitely could get it by summing forces in the X direction. In fact, it would be 65 kilonewtons pointing to the left. So here we would make a summary, and we would say FAB is 0, FAC is 65 kilonewtons in tension, and FBC was 32.02 kilonewtons in compression. And again, if just like a previous example, if we wanted to draw a total member free body diagram, we could in a similar way that we did the previous example.